Hi, everyone. Welcome and thank you for joining our first Particle Classroom series, Introduction to Particle Analysis. My name is Julie Chen Nguyen. I'll be facilitating today. All right, so it's my pleasure to introduce you to today's speaker, Dr. Jeff Bodycomb. Dr. Bodycomb is our product line manager for particle characterization. So he received his PhD in material science and engineering from Rutgers University. He's also quite a bit of a nature lover, tree hugger, and a mountain climber. Okay, Jeff, the floor is yours.
Thanks for that introduction. Anyway, my name is Jeff Bodycomb, and today I want to give an introduction to really particle analysis. And this is a fairly introductory talk, not getting into details, but giving you an overview of the field and kind of what's going to be a little bit interesting about it, and what you should start thinking about when looking at results or planning experiments or communicating results. So first, why are we here? Why are we interested in particle size? And size really affects material behavior and processing across a number of industries. If you take a block of aluminum that weighs about 5 pounds and plop it on my desk and sit there and do nothing, you grind it up into 1 micron powder and you have quite a significant explosion hazard. So just the size changes how that aluminum behaves. And so you'll see it come up in ceramics and ceramic manufacturing, construction, building materials, oil and rubber, both oil extraction and oil refining, all sorts of fine chemical manufacturing, which stumbles into pharmaceutical, food and drink, battery materials, and so on. So it appears in lots of places for various reasons, but it all comes down to the fact that often the size of things matters as much as what it's made of. For example, if you look at pigments used in printing, there are kind of talk about pigment hiding power, which is how effective is that pigment at blocking a background image. So one approach is to grind your pigment, and then you use the pigment to make a line across a test sample, and someone looks at it and says, okay, that is opaque enough to block out the background, so that, we're done with our grinding process. Well, this depends on a skilled operator, and you need to wait for the ink to dry, if you will. If you look at particle size, you'll get similar information, but you get it very, very quickly. And so the first advantage is it's fast. There's no need to wait for drying. The second is that it's operator independent. You don't need a skilled operator. Generally, the folks who are skilled enough to look at the piece of paper and say, hey, that ink is done, you really want them off somewhere doing something much more useful than staring at ink drying. And so you can make these sorts of plots, like I show on the right, of geometric mean size as a function of grinding time, measured by laser diffraction, and the hiding power as a function of grinding time. And you see a nice correlation, say, okay, I can grind for about half an hour, and I'm done with this formulation, or whatever their target is for these particular materials. Okay, so now I've kind of talked about why we want to look at particle size. Let's start defining some terms. Start with the easiest, which is designations of size. Most commonly, people talk about particle size in terms of microns. Here I have a log scale across the top, going from angstroms up to a meter, and micron is 10 to the minus 6 meters. So the most common units, again, are you most often hear microns. As you get to much larger materials, there's a few items where we talk about millimeters, but not many. And then as we go smaller, particularly submicron, people like to talk about nanometers as 10 to the minus 9 meters. And that's really in the colloidal region. Quick comment, if you like to talk about your work in a social setting, a beard second is about 5 to 10 nanometers. That's how far a person's beard will grow in 1 second. So if you want to get kind of a human scale to these numbers, think about beard seconds. And it's also described in Wikipedia, so your friends can go look it up at home if they're curious. Okay, so now that I mentioned these size ranges, let me mention kind of different applications and different names for them. So on this slide, I have size across the top on a log scale, some names for the size regimes, some applications, and some measurement methods. This is something to kind of keep in mind or go dig up if you are starting to look at analysis techniques. At the smallest size ranges, you're looking at electron microscopy, dynamic light scattering, particle tracking analysis, which hasn't made this graph yet. Laser diffraction covers a lot of that range that seemed to win in the previous poll, that 1 micron to 50 micron regime. As you move into larger stuff, you'll start taking pictures and using optical microscopy. And as you get larger, you can even use sieving, although I find it irritating. So I talked about size, but I didn't really define it. So here's a basic question. What is the size? So if I have this tooth-shaped particle, the first thing you want to say is, well, I might measure it the short way or the long way, or I might take a diagonal. Which of those sizes is most meaningful for my application? That's one way of looking at the question of kind of what size do we want to talk about. Different size definitions will give you different results. So kind of jumping the gun a little bit on techniques, if I plot a size distribution as a cumulative distribution on the left, as a function of particle size on the bottom, and you'll see in the upper right, I go up to 100%. So 100% of the particles are less than 3 millimeters. And about 80% of the blue are less than about 1.5 millimeters. So that's how you read these graphs. This is actually the same image analysis data set, but done, analyzed with 3 different size definitions. And I really get 3 different sets of size results. They're all correct. It's not because of a different sample. It's not because of different data. It's just the definition that's giving me different numbers. One take home from this is when you're talking to someone about particle size, you want to define what you mean for all but the most vague discussions. So when I say what size are your particles, and you say 1 micron, okay, that's a pretty good discussion because I haven't gotten into details of it. Is it 1 micron or 1.2? Here, that difference between 1 and 1.2 is a difference of definition. I'll set the scales of millimeters. A second comment, and this particularly becomes important with colloidal materials and nanomaterials, is what sizes can you measure in practice? So it's very all well and good for me to go and draw this tooth-shaped thing and measure different edge lengths, but you might find out that you're going to approximate your particle as a sphere, and any analysis technique that's within reach is only going to give you some sort of spherical approximation. And don't despair that a lot of people have done this and got through the day, so it's fairly common, particularly for very small particles. So here's another comment on size definitions drawn really from microscopy. If I take this particle in the powder blue that's irregularly shaped, you often hear people talk about Faraday, which is a size that's measured by calipers. An equivalent spherical diameter, which is going to be the diameter of a circle with the same projected area as the particle that you've imaged, and so on. And then Martin's diameter is you take a line bisecting the particle area, and you see from this edge to that edge, that edge of the bisecting line. You also see the particle width, which is related to the shortest distance across a particle. In microscopy, particularly older microscopy, you're going to be talking about particle orientation affecting the results. So if a particle is kind of laid out horizontally, you get one number. Vertically, you get a different number. Modern automated image analysis systems will measure, say, the Faraday, which is the size measured by calipers, in multiple directions and return the largest or smallest, whichever you ask for. And so this orientation effect has kind of gotten out of the discussion in particle analysis with the advent of modern systems. So let's move into a few more of the basics. Let's start with the particle. And I've already kind of mentioned very quickly about 4 different ways to talk about size. Now, if you look at a real particle sample, and I use microscope images because they're easy to see, and I have a lot of them. But this applies for even submicron materials that I can't look at with an optical microscope. There's some big particles and there's some small particles in the sample. So if you go and buy yourself some table salt, you'll find out it's all sodium chloride. And then you'll find out that some of the grains are very large and some are very small. And so we have to talk about particle analysis or particle analysis results in terms of distribution. And so what that means is that I've measured one particle here at 4 microns, And then I have this distribution, so I'm going to report a graph with the particle size along the bottom x-axis, and then a cumulative distribution, which is this kind of S-shaped thing that climbs up to 100, or a differential distribution, which is this thing with the peaks and valleys. So I can now talk about samples. Is it monodisperse, where they're all the same size, or polydisperse, where the particles are of different sizes? The only thing that you really find often that has all the particles the same size are particle sizing standards. They're specifically manufactured to be all the same size. You'll also find it in, say, purified proteins and some purified viruses, although cells certainly don't spit out all the viruses the same size. And the ones that aren't the same size aren't particularly active. So most samples have a wide size distribution, and really we're going to really think about most materials as having some sort of distribution width. Well, I'm drawing these graphs, and I have to get more and more careful as I walk through some of these ideas. You'll see graphs with a logarithmic scale. This should be 1, 10, 100, or a linear scale on the x-axis. And logarithmic scales come up quite often, and you can see that these two graphs of roughly the same data look quite different. And so if you're staring at two graphs, say from two different analyses of the same sample or two samples that should be related, one of the first places you want to look is how the graph is labeled. Is it a logarithmic x-axis or a linear x-axis? Second, and less confusing, is that you'll have different displays of a distribution. So here I show volume. I will get into what that means shortly as a function of particle size. And I might decide to show it as a cumulative distribution, this dashed blue line that rises from 0% to 100%. And what this tells us is I can look across here and say, well, 100% of my measured particles are smaller than some particular size. And if I go halfway up, 50% of my particles are smaller than some other size. And if I go over here, about 10% are smaller than this lower size. You can differentiate that cumulative distribution to obtain a differential distribution, and that's that dashed red line. And so you can see a lot of this language comes from statistics, where we also worry a lot about distributions. Another approach is to plot the data as bins as a histogram, shown by the blue bars. So histograms are nice because they remind you that we're working with generally finite-sized bins. They also work well with sieving data. They don't overlay so nicely when you make graphs trying to compare different sets of results. And so I'm somewhat partial to differential and cumulative distributions for displays. So here are some displays from the HORIBA LA960, and really you can adjust, for at least for our analyzer, you can change how the data is displayed depending on what you like, or often more important, what your boss customers like. If you have a distribution, then you'll want to have some way of talking about it. And the first would be kind of the central value. So where's the middle of the distribution? Where is this located? Most often when you think about that, you'll talk about means as a weighted average particle size. You can also talk about medians, where half the particles are larger or half of the particles are smaller. And the mode, which is the location of the peak, or kind of the point where you have the largest number of particles in that particular bin. So in this graph, I've shown frequency as a function of size, and I've said, well, the mean, median, mode all line up. And that only happens because this is a symmetric distribution. Okay, so I started saying, well, particle size, you have to define it. There are multiple particle sizes for one particle. Now we have multiple different particle sizes in a sample. Now I'm going to say, well, what does mean mean? I talk about the average. So if I have three spheres with diameters of 1, 2, and 3 units, let's say microns for the sake of discussion, what's the average? Well, you might say it's 1 plus 2 plus 3 is 6 divided by 3 particles, that gives 2. And that's what's known as a number mean. But there are multiple ways of adding this up. I can weight my results by the number of particles in each size class. I can add these up, by the volume of particles in each size class. And there are a few other definitions in here, I'm going to comment, they all have names. None of these calculations are wrong. They're different techniques and they tend to be used in different applications or due to different history. The most common you'll run across are number weighted means and volume weighted means. Let's explore that a little bit more. Oh, before I do, you might hear about moment ratios. Just a quick couple equations for your reference. These slides will eventually be available online. So the volume-based mean is really the most common, and it does tend to emphasize detection of large particles. And volume-based is important because you're calculating how much material is in each size class. And while I say that particle size is important, the mass of particle in each size class, which comes out to volume mean, plays a big role. So here I revisit those central values. Quick reminder, we have the weighted average as the mean, the median half larger, half smaller, and the mode, the peak position. If the peak is asymmetric, then your mean, median, and mode will all have different values. And you see that D43 tends to be more sensitive to larger particles. Most common statistics, so this is differential distribution. The median, DV50 or D50, half the particles smaller, half the particles larger. By saying V, I mean half the particles by volume or half the particles by mass are smaller and half the particles are larger. D10 says 10% of the particles are smaller than this particular diameter. So that's a way of talking about the smallest particles in a measured distribution. And D90, 90% of the particles are below this size and only 10% are larger. And that's a way of talking about the largest particles in the population. D43, volume mean, is sensitive to large particles, and D32 for smalls. In red, I indicated D100. Please don't talk about D100 for an analysis because you will get yourself into trouble. And the particle sizing police won't come and find you, but what will happen is if you have a 55-gallon drum or a tanker or a train and it's full of particles, you say, well, D100 is 500 microns. Well, that means you figured out a way to measure every darn particle in that gigantic container. Very hard to do, particularly if you have very large particle population, particle samples. So you really want to set your specifications and your discussions around D90 if you possibly can. As you move closer and closer to D100, your analytical measurements become more and more difficult. Of distributions, and they have widths. So I have this peak. Is it fat? Is it thin? Common expression of that is if you think about a Gaussian distribution, you'll talk about the standard deviation. It's a little bit irritating term because you'll talk about the standard deviation of a distribution or report it, and then people will confuse that with the standard deviation of repeated measurements as one measure of experimental uncertainty. It's the same name covering two different concepts. So just keep in mind, it's the same idea. One is the standard deviation of the distribution of particles, and one is the repeatability of your measurement. Both are important. Kind of have to be careful talking about them. You could also talk about width in terms of polydispersity index, span, geometric standard deviation, variance, and so on. Quickly for your reference, I'm going to read one line off this and keep moving. Typically, span is D90 minus D10 over D50. There are other definitions out there, so you do want to define it as you talk about it. Really saying my biggest minus my smallest divided by my median particles. Kurtosis is how sharp is the particle peak, how sharp versus how square. I have not seen this come up in particle analysis. I have seen it come up in statistics more, and I've had colleagues who mentioned it a few times, so I leave that slide in there as a definition. Okay, so now we have a bunch of ways of talking about our distribution or a bunch of concepts kind of kicking around. Go back to number versus volume. Say I have 9 particles, size 1, size 2 microns, size 3 microns, and the volume of this is 4/3 pi r cubed is 4, 32 each, 108 each. Okay, so if I make a plot, percent by number as a function of size, all 3 bins have the same number of particles. But if I look at the volume of particles in each bin, the volume of the 1 microns is quite small, 12, and the volume of 3 micron particles is quite large at 324. So you see this graph on the right, percent by volume as a function of size, you can see it start small and steadily increase. That gives quite a different impression. Again, same data, emphasizing different things about the distribution. So if you're worried about the mass of particle in each size class, this volume distribution is where you want it to be. One of our customers came up with a nifty idea, which was using beans to make this concept easier to see. So you take some black beans, these are lima beans, and those gigantic white ones, and we're going to say, well, let's make equivalent volume distributions. So these beans will all fit into those volumetric flasks. So you can see the number of the white ones is quite small. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. A zillion green ones and half a zillion black ones. So by number, they're quite different. And there's the beans in the volumetric flasks, volumetric cylinder, sorry, showing you that it's the same volume. Now let's go back and take the same number of each. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of each size. Again, look at the volume. Hey, same number of each, but these white ones dominate by volume. So if you were going to go and make soup, you would find out that the white beans would dominate the flavor compared to the green ones. So the green ones and black ones are basically spice, if you will, for this sort of soup. So here's kind of a sketch of a complicated distribution where I have the differential distribution as a function of particle size. And by number, you see the peak is on the far left. When I convert it over to volume, the peak is moved to the right. And if I do the calculation by area, which is similar to the transition from number to volume, but instead of cubing, you just use squares. You have a peak in the middle. So the mean by volume, the volume weighted mean, sorry, is 13 microns, but the number weighted mean size is 0.4 microns, again for the same data. Median shifts similarly, 11.6 to 0.3. Standard deviation by volume is wider, 8.3 microns instead of 0.4 microns for the number distribution. Well, there are some issues with distributions that you want to be aware of, and kind of why do we talk about volume distribution so much? And here's some references. The question comes up, does the mean match the process? Look, in particle analysis, we're keeping score. And so if the number we report doesn't match something that people can take action on and make decisions about, it's not as useful. So often you're monitoring a process, whether it's milling to produce size or agglomeration for size growth. Say, does the calculated mean diameter describe the change to the process? Well, that kind of depends on what you use. So here's a size reduction scenario. We're going to take 10 1 micron particles and one 100 micron particle, and I'm going to mill it. And as you can imagine, the big one gets hit first. So those 10 1 micron particles survive, but that gigantic one, it breaks into two particles of equal volume at 80 microns. There's a slightly magic mill, and the round particles stay round. Let's take the number mean. 10 particles, size 1, one size 100. So in the beginning, my number mean is 10 times 1 plus 1 times 100 divided by 11, which is pretty close to 10. I break my large particle. My number mean goes from 10 times 1 plus 2 times 80, about 160, divided by 12, because I have one more particle because they broke. And the size is 14. So wait a minute, the size went by 40%. And this is on paper. We know the particle broke. What if I use volume? Again, the same start, 10 of size 1, 1 of size 100. 10 times 1 to the 4th plus 1 times 100 to the 4th, divided by the total volume of the system, gives me a volume mean of about 100 units. The volume, the large particle breaks down to 2 of 80, and that's the conserved mass, as I mentioned. I calculate the volume mean, and it comes out to about 80 units. So this is the expected behavior. So you can see the problem pretty quickly here. Number mean has gone up during size particle breaking, and the volume mean has gone down. So really, if I talk about my results in terms of volume mean to the process people, they understand pretty clearly what is happening. If I use number mean, there would be an awful lot of confusion. Now let's try an agglomeration where I have 10 1 micron particles that are preserved, and I have 10 46.4 micron particles that agglomerate into a single large 100 micron particle. So my number mean 10 is size 1 plus 10 times 46 over 20, about 23 units. Then I have the agglomeration. My number mean has gone from 10 to size 1 plus 1 to size 100 divided by 11 to 10. I've gone from 23 down to 10. So my number mean size has gone down by about 50%, actually more than 50%. I bet you know where this is going. If I look at the volume means, my initial volume mean is about 46.4. That's 10 times 1 to the 4th plus 10 times 46 to the 4th, divided by the overall volume of the system to get 46. I take that agglomerate, again, I calculate the volume mean of 100, and this shows the expected behavior. I've gone from 46 to 100 units. So all makes sense to everybody concerned. So repeating, using number mean on agglomeration, you can watch sometimes the number mean goes down even though your large particles are agglomerating, while the volume mean tends to go up. All right, so this is not really a party trick topic. The Beard second comment's much more fun at parties than the whole business of breaking particles and trying to calculate means. I've tried it, just trust me on that. But more seriously, people have done experiments that I thought I broke particles, but the mean has increased. And that's been a real experience. And it's happened to a colleague of mine. So you really should be aware it can happen. So when you talk about distributions or looking at results, kind of look at the whole distribution if you can. Think about which mean you're using and if there are any new kind of calculation nightmares hidden in there. All right, so there is a comment about the methods of analysis, about the all the calculations and expressing results. I want to go through methods of analysis, and later talks and other talks I've given in the past have gone into great detail on the major methods, if you will: laser diffraction, image analysis, dynamic light scattering. And so I'm going to kind of focus on some of the things that don't come up as often, and just to give you an overview of the field. Now, the method is important. If you use different methods, you're going to get different answers. And many people use different kinds of instruments. So it's important to say, hey, I got this number, but I use a Pigment gauge. And that's going to be important when you're comparing to laser diffraction or even deciding if you want to. And so you want to kind of understand what other methods are trying to do, and so you can compare data between your lab and other people's labs. Okay, this kind of ties back to my graph of size range by technique. And then I'll throw in here, as we start talking about methods, you can add more axes or have diameter on the bottom, and then say resolution of size components and mixture for different techniques. So for example, dynamic light scattering does not do a good job of resolving mixtures of components, whereas nanoparticle tracking analysis does. So it's kind of a different instrument, even though it covers the same size range. So when you talk about which size, laser diffraction will give you the equivalent spherical diameter, or really the diameter of a sphere that scatters like your particle. And dynamic light scattering will give you the diameter of, or radius of a sphere that diffuses like your particle. Image analysis gives you all sorts of options based on your photograph of the particle, and so you just have to kind of decide which one makes the most sense. And acoustic spectroscopy will give you a different sort of spherical diameter that corresponds to how the sound interacts with the particle. A few quick definitions, particularly if we get into microscopy. You'll hear people talk about acicular, needle-shaped particles, angular, which means they have angled edges, fibrous, which is what are like fibers, and so on. The Pigment gauge. This is just a nice, elegant kind of device. You have a device with, you have basically a block with a tapered center channel. You place a slurry at in the channel, and you draw a straight edge across it. And the Pigment number is the point where particles start to disturb the smooth surface of the slurry. So as you drag this slurry across, the channel is getting more and more shallow. It's tapered. And so eventually it's so shallow that the particles break the top of the surface, and it kind of makes the surface all broken up or disturbed. And that tells you about the largest particles in the material. So you only get information about the largest particles. You don't get any distribution information, but at the end of the day, it's a block of steel, which is kind of impressive. If you were to take your block of steel and punch about 4 zillion holes in it, you would get a sieve. There are much cheaper ways to make them. So Retch Technologies makes them, I should say Retch makes them, and they use screens. These are very common, they're very old. They've been around for probably millennia. You have a screen, you shake it, and you see how many particles pass through. Those particles are smaller than the hole size of the screen, and the ones that are stuck on top are larger than the hole size. So you're really getting the size of a particle that passes through a hole in the screen, which can give you some interesting results when you have rod-shaped particles, for example, or very uniform spheres that are stuck together as dimers. They work for solid particles. Size is about 30 microns and up. Advantages, very low initial cost. So you can buy a stack of sieves for a reasonable amount of money very quickly. It's very direct. It's very easy to explain to people, hey, these particles pass through this hole. And there's no real practical upper limit to the particle size. Disadvantages, limited lower range. So very small particles are very difficult to work with in these because getting the particles go through the holes can be a challenge, and making holes that small can be a challenge. At least expensive. It's very time consuming. Not only do you get to shake the sieves and spend the time doing that, you find out you get to spend time washing sieves. So this leads to high labor costs. So when your expensive lab tech is washing a lot of dishes, it's not a lot of fun. You need a fair amount of material. And I didn't write it up here, but another disadvantage of sieves is that you are beating on your analytical instrument with your particles, kind of by definition. There's no way around it. And so that means that your sieve openings will tend to change with time. So if you're running something like glass, that can wear wires quite quickly. And conversely, if you're running something like milk powder, it's very delicate, those wires can mill your powder as you shove it through the holes in the sieve. Okay, the electrical sensing zone. This is a fairly well-known particle counting technique, and it's actually implemented in the HORIBA medical division for analysis of blood. You're looking at the change in conductivity and aperture as a particle goes through it. So you have a hole, and there's electric field applied, a particle goes through, and the conductivity changes. And so you'll see it jump the current. It does require conducting liquid, and it measures particle counts primarily. It's very high resolution, and blood cell counting is by far the largest application of this technology. Another related method is light obscuration, where you're flowing liquid through a channel or a pore. You have a light source, and when the particle passes by, it detects it as kind of blocking the light from the detector. So this is nice because it gives you particle count. Use it for USP 788. Gets you high resolution because you're looking at each particle one by one. It does require fairly dilute systems, and that can also slow the system down because you have to wait for each particle to pass, and is prone to cell clogging. And that is, if you have some large particles come through and they start to stack up in this pore, well, you got to stop and clean everything out before you proceed. Sedimentation really takes advantage of Stokes' law and the fact that particle settling is controlled by the gravity on the particle, forcing it down, and then viscous drag, which slows it down. And all that depends on particle size. So if I start with the same density material in a viscous medium, kind of shown here, and those red ones are small particles and the blue ones are large ones, the largest particles will tend to settle most quickly. You can drop a giant rock and a small rock into a lake, and you'll see a similar effect. The big one hits bottom first. So this gets at hydrodynamic size, which is similar to dynamic light scattering, and fractionates the system. It tends to be a very slow technique. Another issue, particularly as you get a small particle size besides time, is that when Brownian motion has a bigger effect than gravity, then that's going to start to really affect your results. Dynamic light scattering, which we have talked about in the past, and we'll talk about more later on in other talks, is probably the most common technique for submicron sizing. Really looking at how a particle diffuses in a liquid, and so it's really thermal energy that makes it want to move, and viscous drag that makes it slow down. And so big particles will tend to diffuse more slowly than small ones. You have a signal that's random because of random particle motion. Interpret it in terms of autocorrelation function, and then get diffusion coefficient, and from that extract hydrodynamic size. One concern here is it really is density dependent as you get to larger particles. When settling becomes the dominant motion, probably time to move on to other techniques with larger particles. Another technique is manual microscopy. And here, just take your classic microscope, and I can count how many particles I have, use a graphical domain, obtain the particle size. Note here that with the manual technique, you're probably going to have some orientation dependence. And you repeat this for a number of fields of view. You really have to go through hundreds of particles. It's simple, it's inexpensive equipment, and you can see particle shape. Disadvantages is it's slow, it's tedious, you don't see very many particles, and if you have a distribution, you need to see a lot of particles to get a sense of what the distribution, how the distribution really behaves. And the labor cost can be pretty high. Automated microscopy addresses that by hooking up computers, and there are kind of two ways to do that. The first is static, where I have the particles on a slide, and I move the slide around beneath the objective, take pictures of each field of view, and analyze the images. Or dynamic, where the particles flow past the cameras. To get around some of the field of view limitations, you can use two cameras, in fact, if you really want to get full information on distribution. In microscopy, you can think of it as 4 steps: image acquisition and enhancement, and that's really kind of how do we get the particles in front of the camera, and then how do we take the pictures? Do we use 2 cameras to get the range of particle sizes we need for a typical sample? Do we use automated stage, and so on? Thresholding and image processing happens in the computer, and then you have a final measurement result. Advantages: it gives you much faster results than manual image analysis. Because I have lots of particles, particularly with a dynamic image analysis system, my results are more statistically sound. I have high resolution for larger particles. I have particle pictures, and look, people like pictures. Disadvantages: they're more expensive, and so that initial cost can cause people concern. It often is made up for, though, by the savings in labor compared to Civic. And then knowing which numbers are important. I can run an image analysis experiment and have results with half a dozen numbers and say, well, which one matters? And somebody has to sit down and say, well, this is the one that's most important for you or most likely to be important, just at the very least to avoid confusion. Acoustic spectroscopy, as the name suggests, is using sound to extract information about particles. So we're going to measure the attenuation, how much sound energy is lost as a function of frequency. So I can accommodate high sample concentration, so there's no dilution required, which is nice compared to a lot of other techniques. I have learn a little bit about rheological properties, and I can also look at zeta potential or particle charge. The disadvantages: you do need a higher particle concentration. You need to know something about your particle concentration. You need a fair amount of material. Laser diffraction is probably one of the most popular modern techniques for particle analysis. Here, we shine a beam of light on the sample and look at scattering as a function of angle, and from that, extract the particle size and size distribution. It's fast, it's repeatable. You can get systems to work with dry powders or suspensions, so it's the most common, and we'll be giving a webinar on that in the relatively near future. And let's see, okay. So I guess some of the key points is, first, when you talk about particle analysis, remember, it's really about distributions. And so when you're talking about your results, kind of keep in mind that not all your particles are the same, even if you report a single number as an average particle size. And so this will help you at least decide whether the distribution width is important, and if it is, you can go chase the number. As you get into more and more precise discussion, be more careful about how you define your terms. Say volume, is that a number mean or a volume mean? Is that D50 or is that the mean size or is it the mode? You know, if it's a very rough discussion, I need something about 1 micron, 2 microns is fine. Don't worry about it. But if you're specifying product or you're buying something, be specific. It'll help everybody. Different techniques can give different answers from the same material since they measure different things. All these results are correct, and one common recommendation is you measure a size by 2 orthogonal techniques so that they confirm each other, and you want the results to be close but not exactly overlay. If they exactly overlay, it means either you have all the spheres the same size or there's something really strange happening. So when you want to talk about results, you might say, look, I've measured these particles. They're 200 nanometers by laser diffraction. And so that tells me, okay, it's a laser diffraction measurement, not a dynamic light scattering measurement. If all I have is DLS, I won't expect exactly the same number. Okay, I'd like to thank everybody for their time.
Thank you, Jeff, for the excellent webinar. Looks like you cover a lot of techniques, and we still have a few questions that came up. For instance, question one, our audience wants to know, how do you know if the PSD result is of individual particle, or agglomerated particles?
Okay, the short answer is you don't. Okay, and the longer answer is, I'll start by saying that's an excellent question, and that's the sort of discussion I want to encourage with these. If you have particles that are agglomerated, most techniques will treat them as a single larger particle. So I mentioned hydrodynamic size, which is really, or say in sedimentation, dynamic light scattering, or your viscous drag term. And the drag is set by the size of everything that moves together. One technique I didn't mention is you can use line broadening in X-ray diffraction for metal particles, which really looks at the size of the crystallite, if you will. So if you have a bunch of those stuck together, you do X-ray diffraction, you could separate them out. But that's the exception I can think of. If you're doing microscopy, you as a microscopist might decide, hey, this is two particles touching, even though it looks like, because it looks like they're two particles touching, you just don't know whether they're stuck together or not. And so that comes down to a human judgment or an equation you punch in somewhere. So generally you can't tell agglomerates, and you need to break them up either with energy or with chemistry.
Thank you. Question two, for ceramic particles that don't get along with water, I think hydrophobic, what method of size determination would you recommend?
Well, so there are two ways to approach this. So the first is, I want to remind you that you don't need to use water. So you could take the ceramic particles and measure them dry. And so you can do dry measurement with laser diffraction or image analysis fairly readily. If your particles are in a slurry, and let's say they're an IPA, okay, and so you know they like IPA, you can actually do laser diffraction measurements or image analysis measurements or dynamic light scattering in isopropyl alcohol. You have to ensure the system you're using will survive the isopropyl alcohol, because it really is a bad day at the office when you dissolve a plastic cell inside an instrument. You have to go have someone fly out to fix it for you. So you check chemical compatibility, but quite often you can use organic solvents to do your analysis. Organic solvents get expensive. So another approach that is fairly common is to say, well, it doesn't like water, but if I add hexametaphosphate, if I add phosphates to this system, then it will like water, and I can go ahead and make my measurement, or if I can add a surfactant. And so that way you can get the low cost of water with the analysis of the water hating material.
Thank you. And this one says types of error when making incorrect assumptions like sphericity and reflected index.
Okay, so I actually have a 45-minute talk or half-hour talk on refractive index. So we're going to set that aside for later on. So I'll just, so a quick comment is that refractive index errors can come up. In terms of this spherical assumption, it depends on why you're making your measurement. So if you try and get from spheres, if you look at particle surface area via particle size and use a spherical assumption, it's going to depend on how porous your particle itself is. So my answer to both is it depends.
And this is only our first class of the 6 classes series that we're going to do. And so maybe we can stay tuned and get that answer later.
Yep. Thanks for, yes, Julie's absolutely right. And I should mention that. I am planning to do a laser diffraction webinar as part of the series. And that will cover RI a lot.
Cool. And then in the interest of time, I'm going to add 2 more questions. What parameters shall we look at to assess the quality of the measurement?
So the first one would be repeatability. So do I get the same number twice? And even better would be to make sure that if I give you a bag of sample, you can take one piece of the sample, measure it, and take another piece of the sample, measure it, and get the same answer twice that way. And that goes into a whole discussion of sampling and large containers. which we will talk about later on in this series. So the first thing I like is, do I get the same number twice? Okay, the second is, do I get a similar number with another technique? So let's say I take my example, dynamic light scattering and laser diffraction. If I measure 450 by DLS and 2 microns by laser diffraction, I know something went wrong. I don't know what yet, but at least it tells me that I gotta pay attention. If I measure 450 by dynamic light scattering and 550 nanometers by laser diffraction, I say, hey, that's pretty close. I'm gonna say that those are good numbers. So I'm looking for consistency across techniques within reason. So those are the two I would look at for whether results are good.
Thank you. And then the last question, in which areas of biomedical researches is particle size characterization most widely applicable?
Oh, that, I can't really say all of them, can I?
The
So,
end.
yeah, there you go. Okay, so, all right. So within biomedical research, going all the way to the applied end, you use particle size analysis and particle analysis in pharmaceutical manufacture. And that's going to affect dose uniformity. The width and size distribution of API can affect dose uniformity. It can affect size distribution, can affect how pills pack in a tableting operation. You can use it to track the coating operation in multi-particulates. If you look at emulsions or emulsion type pharmaceuticals, again, the droplet size will affect how quickly the dose goes into the body. If you're looking at preparing protein formulations, particle size will be a way of telling you if you have aggregation of your proteins into things that will excite immune response, which you don't want. If you're looking at adjuvants or vaccines, particle size will tell you whether your adjuvants can be the size to provoke immune response again. I've seen particle size used for so particle concentration is used in virus production to look at manufacturing yields. That's what I can think of offhand. So I don't know if everything is going to be an easier answer, but there you go.
Thank you. And everyone, please don't hesitate to reach out to us. In the interest of time, and we're going to have to stop right now, but you can definitely email us or reach out to us at labinfo@horiba.com for any questions or even the feedback that you have. And for now, have a great day. And thank you, Jeff, again, and we'll see you all next time.